So question 4. An electron is injected at a speed of 7 times 10 to the power of 6. That should say, to the power of 6 meters per second at an angle theta into a uniform magnetic field of flux density 3.14 times 10 to the power of -5 Tesla, and it describes a helical path as shown. And so the diagram down here, you can see it will do this kind of thing. Assuming that sine theta equals 0.6 and cos theta is 0.8, show that the velocity component of the electron perpendicular to the field is 4.2 by 10 to the power of 6 meters per second. That's talking about the the component that's directly vertical, perpendicular to these field lines here. So here's the actual velocity direction, and we're interested in calculating the vertical component that's perpendicular, and in fact showing that it's 4.2 million meters per second. So to do that, all we need to do is take sine of the angle. You can see the angles on this side here. So sine of the angle, which is 0.6, and multiply that by 7 million meters per second. Part B, the time for the electron to complete one revolution in the helix. So what they're asking for is the time for one complete circle to be completed. Now you can think about that just in terms of the vertical component, or if you like, this component 4.2 that is exactly perpendicular, and just imagine it doing a straight circle. That would be the equivalent time that it would take to do one helix. So we're simplifying it down by considering just that component, and we can find that time simply by using our knowledge of circular motion. Oh, I just realized we've missed out the radius, so we'll do that first. So to calculate the radius, part A, we need to rearrange and find the radius formula again. So simply equating the centripetal force to the magnetic force, mv squared over r equals BeV, and rearranging and solving, we end up with this expression again that we've seen before: mass times velocity over the magnetic field strength times the charge, and since they're electrons, we can just use that. Plugging the numbers in, the mass of one electron times the velocity we just found before, the component perpendicular to the field 4.2 million meters per second, and dividing it by the field strength. And I've just noticed something wrong with the field strength. It should be to the power of -5, not 15, I think. In fact, it is already -5, that's fine. So if we plug those numbers in, we should calculate 0.76 meters for the radius. Part B. Now we can use our knowledge of circular motion again here to simply use distance over time, 2 pi r, since we've just found the r, over that time, rearranging and solving for the period t for one revolution, and we get 1.14 microseconds, or if you like, times 10 to the power of -6 seconds. Part C, we're going to find the velocity component that's parallel to the field, so that's the cos angle 0.8 times the velocity, the original velocity 7. We get 5.6 for that component to the power of 6 still, meters per second. So then we can use the time value and this value here. I suppose we could call that Vx, which is along the horizontal direction, if you like, with the field lines. To find the pitch, because that's a sort of a horizontal distance p, so to find that, we just simply multiply that Vx by the t, the period for one revolution, and that should give a reasonable figure. Let's have a look. 6.4 meters. Okay, question 5. Part of a mass spectrometer is illustrated. The whole arrangement is in a vacuum. Negative ions of mass, that should be kilograms, to the power of negative 26 kilograms, and charge, the same as a electron, are generated at point S, which is at a negative potential, negative 3000, so it repels the electrons, of course, across to H, and that container is kept at zero potential relative to the negative 3000. So the potential difference is 3000. Once inside the container, the negative ions enter a region in which there is an electric field of strength, capital E, and a magnetic flux density, which is the magnetic field strength, in other words, of 0.83 Tesla. Now, when in these fields, the negative ions continue in a straight line with constant velocity, and that tells us, of course, that the force due to those two fields are equal and opposite. So, question 5 continued, part A, calculate the velocity of the ions when they reach H. Now, we've seen this before. You can see it's a very commonly asked kind of question, just using EV, well, because we know it's the same charge as a single electron, and equating that to the increase of kinetic energy Ek, and again to half mv squared. Solving for V. So if you do that successfully, just being careful, the mass is not the mass of an electron. It's given as 2.84 times 10 to the negative 26. Putting that into the equation for V, you get the square root of 2 times the charge E times the voltage 3000 over the mass. So you'd get this value, 1.84 times 10 to the power of 5 meters per second. So then, part B, calculate the electric field strength E. And as we've seen before, the ratio of the field strengths must be equal to the velocity. That comes from equating the force of the magnetic field to the force exerted by the electric field. We know they must be equal and opposite because the electrons travel, sorry, not the electrons, these charges travel at on a straight line path. So we'd say BEV equals capital EE, E's cancel out, giving you this. So we need to solve for E, so simply V times B again. That velocity times the field strength, which was 0.83, gives us 1.53 times 10 to the power of 5 meters per second.